Thank you. Good morning, everyone. So today my talk is about, to our knowledge, kind of a new concept or idea to deal with transcranial delivery of ultrasound. And really the motivation behind our concept is coming from the existing challenges with the current technology that's being practiced, if you will, and we have heard many talks on that technology, which relies on a giant, basically it's a giant hemispherical transducer with over 1,000 elements of single beam, if you will, transducer, that all of which are aimed at the skull as more or less normal incident. And really the challenge is if you're coming at the skull at normal incident, you set up standing waves, and these standing waves turn the skull into a resonator. And in turn, it leads to basically heating of the skull and the surrounding tissue, which requires active cooling. And the second challenge is that because of the physical structure of this transducer, the treatment envelope is really limited, especially at the frequencies that is typically being operated. So we try to look at this problem in a different aspect, using physical acoustics, using what we call Lam waves. But let me tell you what Lam waves are. So if you look at the skull is transversely thin. And it's solid, it's dense, it can support shear waves and compressional waves together, namely elastic waves. And Lam waves are basically nothing but just guided elastic waves that can propagate along bounded structures, if you will, like the skull. The key difference between the bulk waves is that it can propagate along the skull rather than through the skull. And so Lam waves have different features. Importance are they are of different types, meaning that what we call them multimodal, meaning that they come at different types. In this figure, I don't have any pointer here, but you can look at the figure. So they are basically categorized based on a displacement. So, and these are the things that we call modes, if you will. So they are different types of these gyros that you can excite, depending on how you basically excite them. And they are dispersed, meaning that the frequency of, the speed of propagation is a function of frequency and the type. But another interesting feature that they have is that they can leak efficiently, which means that if you put them in the neighborhood of a dense domain, such as a fluid or such as a tissue, they can leak. And that's what is indicated in the figure. So, but how would you excite them? So there are many techniques out there. The one of them that seems to be the best one is called the Wedge Technique, which basically literally a wedge attached to it is a piezoelectric element, or if you will, any kind of transducer technology. Starting from the wedge, you come at the skull at a particular angle that you design with a particular aperture that you can optimize for. At the junction of the skull and this wedge, you mode convert into the properly selected guided wave. And then this guided wave will carry the energy for you, and it will hand the energy to the surrounding tissue, which is the brain on the other side. So basically, Lam waves will act as a carrier of the energy, which gets energy from one side and then gives the energy to the other side, if you will. So the advantages of the wedge transducer is that they can selectively excite the modes that we want. They improve the efficiency, and they can eliminate. So this, I guess this movie isn't working, so I'll go back once and come back. So if you will, if you see here, they eliminate the standing waves, thus they reduce basically heating. And an important key factor here is that it gives you more degrees of freedom to handle attenuation, meaning that you can match the attenuation and what we call the leak rate, the ratio at which basically these Lam waves leak into the brain, to basically handle attenuation in a much better way than the normal beam approach. So, and of course the next question is that how would you achieve focusing? This is typically done by putting these transducers over basically a ring and by forming an annular array. And the thing here is that if you control the radius of this annulus, you can basically control the depth at which you focus by just changing the radius of this annular array. So we validated this concept using numerical simulation, of course, the first step. And this plot basically shows the focusing performance of this ideal wedge transducer, which basically we focused through a 6mm bone at 1 megahertz. And we also looked at the robustness to variability in the thickness and non-uniformity of the thickness, which is basically quite a bit of issue in transcranial ultrasound. And also, we look at the temperature elevation. And this figure I would like to particularly draw your attention to is that we are basically benchmarking the normal beam against the wedge transducer. And the figure on the left, what you see basically in these figures you see the temperature elevation normalized to the maximum temperature in this domain. With the left figure indicates that the temperature elevated in the elevated temperature in the brain is in fact dominated by the temperature elevated in the skull. Whereas in the wedge case, the temperature elevation in the bone is basically almost non-existent compared to the one achieved in the brain. So, of course, we are at the earliest stage of this concept. So we try to basically validate this concept using some experiment. For the first step, we emulated the whole wedge transmission using even 1 MHz immersion transducer. We first confirmed basically this mode conversion mechanism using an aluminum plate. Why? Because the attenuation is so low for aluminum plate for the first step, and these figures show how we basically compared to the normal beam. And then we took a piece of skull, real human skull fragment, and we tried to emulate the whole wedge transmission on that, and that figure shows how we perform. So this figure, this measurement setup was a little bit suboptimal because of the suboptimal aperture, because it's the immersion transducer commercial one. We have to build this ourselves, and also the angle was not actually optimal either. So in conclusion, what we propose really a kind of a concept. And we're at the earliest stage to basically move forward from this point on. The important thing here, the take-home message is that this wedge technique, or if you will, mode conversion technique, can potentially reduce the heating, and it can achieve a larger treatment envelope, and it also gives more degrees of freedom to control attenuation. And at the end, I would like to acknowledge our fundings, NIH, Focus Ultrasound Foundation, and the Stanford Neuroscience Institute. I also would like to acknowledge Focus Ultrasound Foundation for the award. And on that note, I would like to thank everyone for your attention. Any questions?
Is there a quick question out there? Looks like there may be one. Well, Jeff, you're first, but we'll have to go quickly. It's break time.
So we saw in the simulation the wave transmitted, but what about the reflection of the
So
wave?
we designed, that's a very excellent question. So we designed a wedge to minimize that reflection. So that wedge, the aperture of the wedge is designed to somehow balance the amount of energy that is encoupled and the energy that is coming out. So we optimized, there is a reflection for sure in the wedge, but we optimized the wedge length to minimize that reflection and to transmit all the energy. So you look at the efficiency of the wedge transducer as a function of aperture, it peaks at some point, which is like 1.26, if I remember correctly. And at that particular aperture, the efficiency is about 80%. But it drops after that.
Okay, quickly.
What happens to the Lam mode when you've got a real skull where you've got these cortical plates and the cancellous bone in between? So we can get by with an effective medium if we go normal incidence, but I think when you're coupling into these sort of structural waves, the details of the skull may start to play a significant role.
Right. So the result I showed, that's an excellent question too. The result that I showed was for the real skull, the skull fragment that you saw. And guided waves can propagate through composite, if you will, porous materials too. The whole thing, like given a material, like for example, if you're up in a CT scan or something, there is a way to construct the Lam waves also for those composite plates or skull. So there is an effective, if you will, the same approach that works for the normal incident to come up with the effective medium properties for the porous skull or for the heterogeneous skull. Same thing works also for the Lam waves. The whole thing about Lam waves is that it combines shear waves and longitudinal waves, which are bulk waves, in a, if you will, in a guided fashion to basically form these modes.
We're getting static here. We really need to take a break. Can we take this up during the break, both of you?
One more thing is that I'm actually presenting a poster later this afternoon. I would be more than happy to discuss this.
So we
with you.
can. I am so sorry. I hate to cut off conversation, but the break is going to be short as it is. So everybody come back soon. Thank you.